and giving us an enolate. And enolates are good nucleophiles, so that you can take electrophiles like halogens, Br2I2Cl2, or alkyl halides like methyl iodide, ethyl iodide, or protons, and do SN2 type chemistry. To give us our products.
Okay, quick question.
Yeah.
Are you going to ask us to show resonance, like in that second step?
Sometimes something I might do is I might ask you to explain something. But taking in the advice from the TAs this semester, from the last exam, I put in things and I explain parts of the questions that say things like, the TAs have been instructed to only read the first 15 words. Anything past word 15 will not be considered. Or particularly, these questions are best answered using chemical structures, not words. So use chemical structures, and if you use words, realize anything past word 15 won't be considered. And the other new thing is, if you say something wrong, it's all wrong for explain questions. Because one of the things why it took so long was people would write 3 paragraphs. And 2 paragraphs may be dead wrong, but 1 paragraph might have been right. And then it's like, so do we give credit for the right paragraph, even though most of it was wrong? And that was really ambiguous, and so we decided let's make it limited to 15 words, which should be more than enough to explain it. It's okay to talk like a caveman. It's okay to talk like a caveman. I'm not saying my test is so easy a caveman can do it, but it's okay to talk like a caveman. And chemical pictures, cave paintings might be the best way to explain some of these answers. So for example, in at least one of the explaining questions, the answer is pretty much resonance. And so, instead of using a paragraph to explain, you just draw these resonance structures and you can go bada bing, bada boom and probably get full credit.
Just write the word resonance.
We'd prefer you to draw it. We wouldn't get full credit unless you actually drew it. Because resonance can mean a lot of things. Which resonance are you talking about? So enolates, which can resonate like this, behave like this, attack Cl2. And the one thing you have to worry about is if you let it go more than once. So you can have it go once. If you had one equivalent, it will just go once. But if you had multiple equivalents, it will go as many times as you let it. So for example, with acetone, if you added 6 equivalents of Cl2, we would eventually get hexachloroacetone and probably be put on the terrorist watch list.
I don't get it.
This thing can, you know what a Mickey is?
I drink Mickey's.
Not the beer. I'm talking about like the 1950s gangster Mickey, which was put in drinks, but for more nefarious purposes.
Oh, okay, I'm getting you now.
Yeah, so the old gangster memes, you'd slip someone a Mickey.
Okay.
That's kind of what this is.
Okay.
It was also partially responsible for Anna Nicole Smith's death.
I have a real question also.
Yeah.
How do you know, I always have trouble, how do I know when the base is going to take the alpha hydrogen or go into the carbonyl? I forget that a lot.
So it depends. So it depends again what the base is.
Yeah.
So in general, taking a proton is easier than adding to a carbonyl. Taking a proton is easier than adding to the carbonyl.
Okay.
So in lecture, up until we talked to enolates, we kind of just glossed over it and we just had it go into the carbonyl.
Yeah.
But in reality, especially if you're more hindered, so for instance, ethanol, so sodium methoxide, it will do both, but it will eventually it will funnel into a thermodynamic enolate. If you add something like LDA, it's just going to do the base.
Okay.
So just get kind of word of wisdom, it is easier for a base that take a proton than it is to add into a carbonyl.
Okay.
So we form our hexachloroacetone, and this molecule wasn't responsible for Anna Nicole Smith, but something similar to this was. I just want to get it right on the internet. That was actually an exam question in one of my exams at Yale, was what was the significance of a molecule similar to this? And they had a picture of Anna Nicole Smith on it. The question was, what does this molecule have to do with this person? Luckily, I trolled TMZ. Not really, but maybe sometimes, and so I do. You too. All right, so if we make this polychlorinated ketone, what's the significance of these side chains now? What can happen if you add in a strong base? They're good leaving groups. So if we add multiple equivalents and we form these polychlorinated stuff, and then we add in a good base like sodium, not a good base. If we add in a good nucleophile like sodium hydroxide, it's just going to kick into this. And of course, since this is under basic conditions, what's going to happen to the proton once the base does that? It's going to become deprotonated. So the product we get out would be the carboxylate, unless we had HCl. And then maybe we could add in, maybe we could add into this again and give us carbonate, but that's a little bit advanced steel.
Would you need two equivalents in order to remove it, or just sometimes the second?
Oh yeah, you would need multiple equivalents. And so if you have enough base to do 3 chlorinations or brominations, you probably have enough base to remove it. And there's also enols. Where a ketone is always in equilibrium with its enol tautomer. So what decides the KEQ of this? So the equilibrium constant between a ketone and an enol, what decides the equilibrium constant, whether or not it favors the ketone or the enol? The pKa of the alpha hydrogen. So the more acidic your alpha hydrogen is, the more enol tautomer is favored. So for instance, under neutral conditions, so H2O, you only see 0.0001% of the enol form rather than the ketone form. So under neutral conditions, you see almost entirely the keto form and none of the enol form. And this is a pKa of about 24, or 20. Conversely, more acidic ketones, which are pKa 10-ish, will almost exclusively be, well not exclusively, but about 80% or so favor the enol form. And that's because it's more acidic, and so under neutral conditions, it's easier for this to take this proton and then equilibrate to give us the enol. So the more acidic your proton, the more enol tautomer you have. So conversely, if you take your ketone and you throw it under aqueous acidic conditions, you can actually convert it almost completely to the enol form. The reason being is under these conditions, you protonate the ketone, and then when you protonate this ketone, you're really drastically dropping the pKa of this. When the carbonyl is protonated, not only is this more electrophilic, this is going to be more acidic. So it's really the same idea way this favors the enol form is when this is protonated, we're making this more acidic, So water can grab this and form the enol tautomer. So under acidic conditions, you can make anything your enol. And the thing about enols is they're a big fan of the song, anything you can do, I can do better. Enols are kind of like the pesky little kid of the enolate. And so just as with enolates and sodium hydroxide, you can do stuff like this and form halogenated compounds. You can do the same thing with enols. And just as before, it will go as many times as you let it go. So for an exam, I think I'll be very clear. If I say multiple equivalents or excess, I'm telling you to let it go all the way. If I say one equivalent, that's my way of saying have it go once.
Dr. Gustafson?
Yeah.
All the way like how you did on the top right?
Exactly. If there's multiple equivalents, it will go all the way. But if you just throw in one equivalent, you can get nice yields for just mono, just going once.
What if
Yeah.
you had like an aromatic group on that side and you said excess, would it only
So your,
add Cl to the,
your question is, would we have a possibility of an electrophilic aromatic substitution?
yeah, like what's,
If there's a Lewis acid, sure.
okay.
So, I think we've done probably examples where we had, where we did done both.
Okay,
So yeah, it's something to worry about.
okay.
Yeah, it turned out chemistry is really hard. I probably have like a 300% reaction working rate, and that's like awesome. It's really like baseball. If you hit 300 over your career in baseball, you're most likely a first ballot Hall of Famer. In chemistry, if that percentage of your reactions work, you're happy. That probably makes us all sound like hacks, and maybe some people will say I'm full of it and chemistry works all the time. Okay, so that being said, if a reaction works once, it should work as many times, right? And so chemistry that works once will work all the time. It's just I'll design a reaction and say, oh, this is going to work great. And if my design reaction works 30% of the time, I'm thrilled. If a reaction that works 100% of the time doesn't work for me, that's my fault. Okay, so from there, we went into strictly enolate formation. Particularly, we started off with the most hard example of enolate formation, which is non-symmetrical ketones. And the reason we started with the hardest case was because if you understand this, then any other enolate formation in something like an ester or an aldehyde is cake compared to this. Nothing changes theoretically. And I introduced to you guys two different bases, or classes of bases really. The first one is lithium diisopropylamide, which is a really, really, really strong base. And that's the key part, number one. Lithium diisopropylamide's got a pKa of its conjugate acid of 38. pKa of 38. Really, really strong. These guys have a pKa 20 to 24. So by, at the very least, 14 orders of magnitude, this reaction is favored towards the product. So in other words, for all intents and purposes, this deprotonating one of these hydrogens is irreversible. Happens once and it sticks. And because lithium iodide isopropyl is also fairly bulky, because it's got two really big isopropyl groups, when we're doing this chemistry, and we normally do it cold, -78 degrees Celsius, it's going to go up to this molecule, and it's going to sample both of these protons without actually doing the reaction, and it's going to say, all right, this proton is non-hindered, no steric bulk, so it's got some elbow room for the isopropyl groups. It's going to go to this carbon, it's going to try to take the proton, but its isopropyl group's going to bang into this methyl group, and it's like no bueno, and it's going to go and take this proton instead. So lithium diisopropyl iodide for that really lame mnemonic device I just made takes the least hindered proton. And because it's such a strong base, and the equilibrium favors the right 10 to the 14th fold or so, it's not going to go back. So it does the reaction once, and what it gets, we get. Bada bing, bada boom. And that gives us the kinetic base. Sorry, the kinetic enolate, which is the less substituted double bond. Conversely, the other base we can use is sodium methoxide. Sodium methoxide is a pKa of roughly 16. So basically, it's going to favor the starting material over the deprotonated product 1 times 10 to the 5th or 6th. So it's going to definitely favor this over this because of the pKa. So what people do is they use a boatload of sodium methoxide to push the equilibrium. 15 equivalents, 100 equivalents. I once used 300 equivalents. It's cheap. So you do whatever, you take ethanol and you throw in sodium metal. Gets a little sparky. But then eventually, when the sodium metal is gone, you have sodium methoxide. More or less. I kind of took out some of the gory details, but that's basically how you make it. So you've got your sodium methoxide, you put a boatload of it in, so the Chatelier's theorem can kind of push the equilibrium towards the base. But here's the thing, it's going to be going back and forth, back and forth. It's going to take this proton, and it's going to go back. It's going to take this proton, and it's going to go back. Then it's going to take this proton, and it's going to go back. It's going to go back and forth, back and forth, back and forth, until it reaches equilibrium. And the equilibrium is going to favor the more thermodynamically favored enolate. And the more thermodynamically stable enolate is going to be the more substituted one because of Zaytev's rules. So because sodium methoxide actually has a real equilibrium, it will actually go back and forth until it funnels through the more thermodynamically stable enolate, which is the more substituted enolate. Texas carbon is a nickname for carbon that you accidentally draw 5 bonds to. Why does this great state of Texas get the connotation? Because everything's bigger in Texas, including their carbons apparently. No offense to the great state of Texas. So we get the thermodynamically more stable enolate with sodium methoxide, and then we get the kinetic enolate with LDA. And then we do all the chemistry we've talked about. X2, Br2, Cl2, methyl iodide, ethyl iodide, any alkyl iodide. And then when we get into chapter 19, then we can throw in things like aldehydes and ketones and esters and so on and so forth.
Will it ever form a triple bond?
What's up?
Will it form a triple bond ever? Take, like the green product?
So
Will it take the second hydrogen?
No, because now the system has a minus charge. It can happen in some cases, but it's very rare, and you usually need something like aromaticity, driving force, or doing it in the surface of the sun. Yeah.
When you're doing the isolation of diketones, why did you use NaH instead?
No reason.
Okay.
So why we use sodium hydroxide rather than, say, diisopropylamide?
Yeah.
So the reason we didn't use sodium methoxide is because the sodium methoxide can add into the acid chloride. And so that's a side product we want to avoid. Because remember, we're using like 300 excess or some ridiculous excess of sodium methoxide. So with that much excess, it can easily add into the acid chloride and then the reaction doesn't work. Could you use LDA? Yeah, you could use LDA. You might worry a little bit about the LDA acting as a nucleophile and adding into the acid chloride. In fact, I may have done that in the last year. I've been like, really? I was surprised, but it can happen. And whereas sodium hydride, you don't have to worry about that. But you know, that's just another kind of layer to think about is, you know, if we're doing a more complicated reaction, will the bases do anything to our reactions? That's always something good to keep in mind, but I'll try to avoid that in the exams. So, anything else in chapter 18 before I get into Clayson? Yeah.
I know you had something in the practice exam, it was like a diketone with 2 equivalents of LDA. If you get a 2 enolates together,
Yeah.
and some kind of molecule, what negative goes into the molecule? Do you know?
I see what you're asking, and so let me draw it up. So, you know, here is the first enolate you form from a diketone, right?
Yeah.
And so, this hydrogen is still basic, is still acidic, right?
Yes.
It's adjacent to the carbonyl, and albeit the carbonyl has a minus charge in it, so it's still acidic, so maybe instead of being a pK of 20, it's a pK of 25.
Okay.
But it's still acidic. An LDA is still definitely strong enough of a base to take this proton. So LDA can definitely take this. And now that gives us what we call a di-enolate. Like so. And so your question was which one of these double bonds is more reactive, basically?
Yeah.
Okay, great question. Phenomenal question. So, which one do you think will be? And give me a reason why.
The left, because I think I saw it in my notes.
This one?
Yeah. But I don't know
Okay.
why.
So, the reactivity of any nucleophile is strongly correlated with its pKa.
Okay.
So the higher pKa, the more basic you are. Sterics aside, the more nucleophilic you're going to be.
Okay.
All right? And so the conjugate acid of this enolate is about 12, because it's between the 2 carbonyls. And the conjugate acid of this enolate is about 25, because it's only by 1 carbonyl. You see that?
Yes.
And so the thing with the higher pKa is going to be the better nucleophile. And so because this has a higher pKa, it's going to react first. And so, for example, if I were to take a diketone, throw in 2 equivalents of LDA, we would get the dienolate. And then if I were to throw in 1 equivalent of Br2, the Br2 would go here because this is more reactive than this because it's less resonance stabilized.
So you just have the negative oxygen go down to the carbonyl again, that double bond move over.
So if you threw in some electrophile like Br2, by some degree, the more reactive, less acidic enolate will attack the Br2 like this.
Okay.
And then that will give us, I'm gonna do it in orange so it pops more. So that'll give us something like this. Where we still have the second enolate, the less reactive, the less nucleophilic enolate in the enolate form, and then you have the more reactive enolate attacked the electrophile and got alpha functionalized.
And you just leave it like that with the counter ion, you're good? That's fine?
Yeah, unless I say H3O, and then reprotonate this,
Okay,
alright?
alright, thank you.
If you did like two equivalents, would it then go to the other?
Absolutely.
Okay.
Absolutely.
Could you use cytosol as like an argument for this one?
For this one,
For,
you know,
previous one?
technically,
Because that one is less substituted, so it's less stable, right?
you know, I like that. It's a little bit more complicated, but technically, you can argue, it's a sound argument, and there's definitely something to it. What I would say, though, is why this, resonance, right? This minus charge is more stabilized because it can go throughout the 5 atoms, whereas this minus charge can only go up through 3. That's perhaps the real reason. But, you know, Cytaf's rules, that's not a bad argument. It's something to think about. But I think the reality is the stabilization from resonance. And the pKa of the conjugate acid. But still, I like that thought. Yeah.
You have a question on here where instead of using Br2 as an electrophile, you use benzaldehyde, and then you treat it with acidic conditions, water and heat.
Yeah.
Is the point of...
So that's an aldol condensation.
Oh, okay. And then that's going to end with a decarboxylation? Or...
It can.
Okay.
So I know which question you're talking about, and then as we were grading the test, we decided that question was way too mean. I even tell the students I apologize for that, even though it was a 2-point question. It was a mean question.
Okay.
And if I ask a question like that, it will be a little bit more reasonable.
Okay.
But yeah, it would be an aldol dehydration followed by a decarboxylation. You got that spot on.
Okay.
Alright, so that takes us to chapter 18. 19. I'll be watching Sesame Street with my kids so I get my numbers right. 1, 2. The count. Obviously the best character, right?
Cookie Monster.
He's no longer Cookie Monster. I thought he was Veggie Monster now.
Is it?
What?
He no longer eats cookies.
And he's
There's something wrong with this.
He's what?
He's angry about it.
Oh, of course. Because he hasn't lost any weight since he stopped eating cookies. So, chapter 19, we're going to be talking about, we talked about the Clayson. I remember in lecture yesterday, I gave some reasonable examples and some reasonable examples. And then I decided to give you guys one of the hardest examples, because I figured if you could get the hardest example, then any Clayson question is going to be cake. So, let's talk about the Clayson first.
Opposite of the book's pedagogy.
What's up?
Opposite of the book's strategy.
Oh yeah? But it's funny because the example I showed, the really hard example, was straight from the book.
No, I was just referring to your previous comment about how, remember, you said how they wanted to make some of the reactions more similar.
Yeah.
To make it easier.
Yeah. But you know, that's a debate to be had.
Great.
There's merits to it, I'm not going to lie, but
I like this strategy, actually. For me,
yeah. My Ph.D. advisor was very big with this strategy, and he would rail on and on and on about how modern organic chemistry textbooks were doing more disservice to organic chemistry by trying to make things more similar to each other than they actually were. I think he actually went in the podcast once saying that. So again, the basic simple Clayson, and again, this is the Clayson under thermodynamic conditions. And unfortunately, under thermodynamic conditions, you are mostly limited to homoclasons. So Claysons between two of the same molecule. I'll get into this the first 5 to 10 minutes of lecture before I get into the aldol tomorrow. I've already talked about the aldol though, in lecture. But if you want to do a hetero Clason, so between two different esters, the answer is thermodynamic conditions. So if you just use Wayne's World, let's kind of rewind it. The Scooby-Doo ending, right? If you want to do a hetero Clason between two different esters, the answer is kinetic conditions. Kinetic conditions, so LDA. And free-forming and enolate, and that's what we'll be talking about a little bit tomorrow. But in general, if you use sodium methoxide and ethanol, this is going to be the thermodynamically controlled Clason. And so what's going to happen is we're going to form the enolate with one of these. And since I drew my sodium methoxide red, let's just have it take the proton from the red molecule. So it's going to take the proton, giving us our enolate. And then the enolate is going to attack an equivalent of itself in the ester form. So an ester crime. To give us a tetrahedral intermediate that's going to look like on these lines.
That's the intermediate you're drawing right now?
Yep. And then you have two options. You can have the O minus kick off the enolate again, and that will be the backwards reaction. So the enolate adds and the forwards reaction give us this. By the theory of macroscopic reversibility, we can kick off the enolate to go back to the starting materials. And that, of course, is what happens in the retro Clason. Remember, with most Clasons, they can go back and forth. Forward is the Clason, backwards is the retro Clason. But I'm just going to draw the forward Clason for now and not confuse anybody. So in the backwards retro Clason, this step we kick off the enolate to go back to starting materials. But in the forward Clason, we kick off the ester. Sorry, we kick off the O8, the ethyl group, ethoxy group.
Are those supposed to be methyls or ethyls?
Okay, I do that a lot, right? That shows you how I feel about ester substitution. They're all the same. But thanks for catching that. In practice, most chemists stick with methyl esters because their methanol is less precious than ethanol. Not by much. But most chemists I know would rather use the ethanol for other reasons. Obviously not in the lab, or from the lab stock, but you guys get the meaning. So this gives us our acylated enolate, so our Clason product, but the reaction doesn't stop here. Because if it did stop here, we could have the ethanol that just kicked off. So add back in, giving us this, which could then possibly do a retro Clason to give us our starting materials back. So luckily the reaction doesn't start there because it actually works. And so then what happens is we form this hydrogen between two carbonyls, so this diketone, we know they're really acidic. But this is under sodium methoxide conditions. So pKa 12, pKa 16, so by 1 times 10 to the 4th, this is going to favor the base deprotonating the acidic hydrogen. Again, this is favored by 1 times 10 to the 16 minus 12, so 1 times 10 to the 4th. To give us our deprotonated enolate. So just like today when I was talking about saponification and saying the thing that drives saponification, basic saponification using sodium hydroxide is the carboxylic acid being formed, being quickly deprotonated under the conditions to give us the carboxylate, and that's what drives going from a methyl ester to carboxylic acid. Same thing here, right? The thing that drives the Claisen rearrangement is the fact that the product's of an acidic hydrogen that's quickly deprotonated, and this gives us a thermodynamic sink. And this drives the reaction away from the retroclaisen and towards the Claisen. Of course, if we had a product that did not have the alpha hydrogen, it would not have the thermodynamic driving force of that hydrogen deprotonating it, and its equilibrium would be lousy and won't give us a good product. So, whereas something like this works great to give us a product that can be deprotonated, if we have another substitution adjacent to the alpha carbon, so that our product doesn't have an acidic hydrogen, the reaction sucks. The reaction sucks. So we need the product to have this acidic hydrogen for the reaction to be driven forward under thermodynamic conditions. Yeah?
If you have two acidic hydrogens, could you do it twice and then leave one, and that would be your most stable product?
Yeah.
Okay.
I can see that happening. I've never seen it happen. And maybe if I drew it up, I'd change my mind. But when you said my mind, I think,
Okay.
it could happen.
Doctor,
Yeah.
is there any reason that it wouldn't go enol the other way?
Oh, it does, right? It's all resonance, right? So we can draw a resonance structure that's going enol the other way. The key thing I would say is we typically draw the enol when we have an ester and a ketone towards the ketone. The reason we draw it like that is because there's a electron donating group and this carbonyl in the ester, and so that's going to slightly disfavor the enolate being here. But it's gonna be a significant contributing resonance structure, so nothing wrong with drawing it towards the ester. And so that led us to demonstrate the power of this driving force of the protonation, which is, and I think a lot of you guys will remember this, because it was only yesterday. Now the Beatles song is stuck in my head, and all I said was yesterday. So, and now it's stuck in someone else's head, I'm sure. You're welcome. So, was this lovely example, where this, which could in theory be the product of an intramolecular Claisen, if we make this and we subject it to intramolecular Claisen conditions, so sodium methoxide, and ethanol. If we take this molecule and we stir it, what we actually get out is this molecule. And if you number the carbons, the one, two, three, four. We find that the number 1 carbon is now the ester carbon, and the ester 6 carbon here is now the ketone carbon. And this equilibrium is going to almost completely favor this guy. And why? Well, the reason is because when we form this guy, it's got an acidic proton that this guy does not have an acidic proton. This has a methyl at the dicarbonyl carbon. This has a hydrogen. Alright, see, I just drew it going to the ester, but I'm gonna let my OCD take over and draw the enolate going towards the ketone. So this guy has acidic proton, so it can be deprotonated to give us a thermodynamic driving force. And so as I said in lecture, the thing that really drives us forward is, well, first off, this is through a retroclason followed by another clason, a different clason.
What takes the proton? Is it PP?
The sodium methoxide. So basically what happens here is the sodium methoxide can add into here. To give us a tetrahedral intermediate like this. And then instead of kicking off the ethoxide to go back to the starting material, it can also break this 1,5 bond to give this as an enolate. So this is just a retroclason. And of course, this isn't the greatest equilibrium, but just remember, this deprotonation step at the end is going to make up for any lousy equilibrium towards, on the path towards it. I do understand. Hold it through here. So we're swimming in ethanol, and we're swimming in sodium methoxide. So since we're swimming in ethanol, we've got this enolate, which is a pKa of 20 something, and we have ethanol. So obviously we can protonate this with the ethanol. To give us the new product. And then, of course, again, we're swimming in ethanol, but we're also swimming in sodium methoxide, and so then we can reform the enolate. And of course, there's going to be an equilibrium between taking this proton and taking this proton, but since taking this proton will give us a product that can be deprotonated, it will eventually funnel through sodium methoxide. Taking this proton to give us now a different enolate. Let me withdraw it so I have more room. So pretty much, first thing we did was a retroclason to give us this enolate. Then we did an intermolecular proton transfer to give us a neutral compound. And then we did another intermolecular proton transfer with the base taking this to give us this enolate. So this is one of those cases where an intramolecular proton transfer probably wouldn't work that well. But since you're swimming in the base, you can do your intermolecular. So we just swapped out this enolate for this enolate. And then just to get to this product, it's just now this new enolate attacking this carbonyl and doing a clason. So then we do another clason that gives us this, and then since we now have an acidic hydrogen, it can be deprotonated, driving equilibrium. So this is just an example of clasons being highly reversible under thermodynamic conditions, and then just eventually giving the thermodynamic product. Okay?
And it's ethanol again, not methanol.
Yeah. If you ever see that, it's me. It's me, not you. According to the state of Texas, I'm dyslexic, so maybe I'll blame that. And that's actually a true story, although I don't really believe it. I grew up in Texas, so that's why I can say it's a great state. Well, I grew up in San Diego, but I was born in Texas. Okay, so the last thing I'll go over in the last 10 minutes is a sneak peek into the aldol. Oh, first off, if you do the clason under kinetic conditions using LDA, everything's good. If you do the clason under kinetic conditions, you get the kinetic product. And so the way you do the kinetic condition under kinetic clason is you use LDA. So you preform your enolate using LDA. And the great thing about LDA is you have this really, really bulky amine. The really, really bulky amine is not going to be able to add back into the clason product. So it can't do the retroclason. So if you want to do clasons you can't do under sodium methoxide conditions, you just use LDA. And the nice thing about using LDA and preforming your enolate is you can now do cross-clasons, heteroclasons, so clasons between two different esters. So if you want to do a clason between two different esters, the answer is LDA. And they'll give us a product like this. And we do not have to worry about it going back because LDA is so bulky, it's going to be hard for LDA to add in and go backwards. And even though this kicked off sodium methoxide, it only kicked off one equivalent of sodium methoxide, right? So do you think one equivalent of sodium methoxide is going to be able to push the equilibrium back with the Claisen? No, you need thermodynamic conditions which have like, many equivalents of sodium methoxide. So LDA is a good trick to know. And so almost perfect timing, I think I have five or 6 minutes, which represents a appropriate thing to review the aldol. So, whereas a Claisen is an enolate, any enolate, plus a ester, enolate plus an ester, an aldol is an aldehyde or a ketone enolate, although any enolate will work, plus an aldehyde or a ketone. So the reason it's called the aldol, and up until I taught this class last semester, I thought there was some famous chemist called Aldol. For some reason I even thought in England he was referred to as Sir Aldol. I thought there was a famous chemist whose name was Aldol, who was Sir Aldol. I really did.
Did you see it in a dream?
No. I just assumed. I assumed there was some Sir Aldol walking around. But when I was teaching class I found out the first aldol ever done was between two different aldehydes. Under acidic conditions. So under acidic conditions, this means this is going to the enol mechanism, right? So mechanistically speaking, one of the aldehydes is going to become the enol. And then it attacks to give an O-, which is going to quickly take the proton under those conditions. And the product you get out is an aldehyde with an alcohol. So when I taught this class, I found out there's no Sir Aldol. It's just the products gave you an aldehyde with an alcohol. And that's how it got its name. So my visions of some Sir Aldol with a top hat and a monocle walking around England saying, I invented the aldol reaction, kind of faded. And so here's one more thing that relates with the aldol. So this, going from the aldehyde or a ketone to the carbonyl with the beta alcohol, is the most common version of the aldol. But if you heat it up under both acidic or basic conditions, you don't get an aldol reaction, you get an aldol dehydration. And what an aldol dehydration is it starts off with your aldol, which you can do under basic or acidic conditions. So acidic conditions go through the enol like this. Basic conditions go through the enolate. So under acidic conditions, you can imagine protonating this alcohol. And furthermore, under acidic conditions, would this aldehyde be in the keto or the enol form? Under acidic conditions, would we want the keto or the enol form? The enol form, right? So we form the enol with this protonated carbonyl. And what happens is you eliminate the alcohol as water. To now get a double bond. So this is the aldol dehydration. So usually under room temperature, you can stop at the aldol product. But if you heat it up, especially under acidic conditions, you can protonate it from the enol, and then through this electronency kicking down, kicking up, we get our double bond. If you want to draw this as an one type mechanism where the water leaves to give us the carbocation and then the electron flows, be my guest. Absolutely, that's perfectly reasonable. Someone have a question? Yeah.
On the very beginning of that equation,
Yeah.
where did that proton go when you turned the?
Oh, magical proton transfer I didn't draw. Alright, so how about this? Proton should be here, and then water formed. And take it to form the enol. Sorry, I forgot the proton transfer step. Alright, so the last thing I'm going to talk about is now the basic aldol and dehydration. Because again, enols and enolates have this really vicious, well not vicious, but they have a sibling rivalry where they like to outdo each other. I just totally personified chemicals, didn't I? So the basic aldol is going to be enolate formation. And the enolate is going to attack a carbonyl. In this case, I'm just going to draw it attacking itself. Another equivalent of itself, let me say. So this would be the aldol product. And so under basic conditions, the dehydration, you would think would be more of an E2 type mechanism. But in reality, tons of experiments have shown that the way we get the dehydrated product, and when we heat it, actually goes through the enolate. So an E2 mechanism would just be the sodium hydroxide taking this proton, doing the E2 mechanism. But what it's found is actually easier to form the enolate first, because this hydrogen is more acidic because it's adjacent to the carbonyl. And so by NMR, what we actually see is before we do the E2 elimination, we form the enolate first. And then we do the elimination through the enolate. So it's basically an E2 elimination, right? But since it goes to the enolate, we give it a slightly different name. So instead of an E2, we call it an E2CB, meaning it goes to the enolate or the conjugate base before it does the E2. That's wonkiness. It's an E2. Unless you're in my lab and you're giving a Ph.D. second year exam at UCSD and I'm on your committee, I'm going to ask you to say it's E2CB. But for this class, it's just an E2. Yes? What do you mean? Oh yeah, yeah. Sorry. Right. Because if you don't do heat, you'll get stuck in the aldol. So you definitely need heat for this. So under acidic conditions, you go through an E1-like mechanism. Under basic conditions, you go through an E2-like mechanism. Yeah.
There's a hydrogen on top of that oxygen, and I don't see how you got that.
This guy?
Yeah.
Fair enough.